You know, I went looking for confirmation about what I've previously just discussed in my prior video of the self-accelerating nature of a reactant or reactance occurring in a circuit, because that's the source of free energy, is the ability to allow a little bit of time, a few, several hundred milliseconds, to be more precise, or less, to allow the accumulation of reactance to accumulate in a circuit, because the more that accumulates, reactance being lossless, you can't spend it, the more quickly it accelerates the reactive process. In other words, it builds up reactive power more quickly the more it accumulates. And so then the ultimate problem is not the creation of reactance, but the conversion of it into useful energy. And of course, Oliver Heaviside solved that when he solved the transatlantic cable, telegraph transmission cable problem of the late 1800s. Well, lo and behold, I went looking on DuckDuckGo, my favorite search engine. I rarely use Google. And immediately, I got the answer I was looking for. And it's Wikipedia article, it's called the self-accelerating decomposition temperature. And you can see it has to do with peroxides, and it's amazing. When the peroxide breaks down, it generates heat. But if the heat should build up and not dissipate rapidly enough into the surrounding environment, if it should build up in the liquid in which the peroxide is located, the presence of the heat accelerates the decomposition of the peroxide. So the more buildup of heat there is accumulated, the more rapidly the peroxide breaks down. And this is why peroxide can explode. That's why it's used as a fuel and as rocket fuel, because of this ability to self-accelerate its breakdown. Okay? Because all you have to do is ignite a little bit of it, and the rest of it just takes off. It just kaboom. So this is very interesting, because although this is not a direct electrical, confirmation, doesn't matter, because everything in the universe has an electrical component to it. And explosives are certainly no exception. I keep going back to explosives as an example, because if you take away the chemistry of an explosive and leave just the electrical nature and duplicate that in a circuit, you'll have the exact equivalent of what goes on in the explosive. You can duplicate it without the need for the use of the chemistry involved. It's the same explosive force. That's why transformers can blow up to the degree that they do, because they have turned into the electrical analog of an explosive device when they do so. Well, here we have to use peroxide for Wikipedia to admit, for common knowledge to admit of this self-accelerating nature to the explosive process. And it's this self-accelerating nature to the explosive process which is part and parcel to reactance, part and parcel to transients, part and parcel to surges. And it's the whole fundamental basis for my study of electrical dynamics, provided by simulators of all things. I have no experience with this thing right up front in front of my face. I wouldn't dare try. But in the safety of the simulator environment, I study it, and time and time again over the period of the last, a few years, I come across this behavioral characteristic of a transient. It's to grow at a logarithmic rate. And here's confirmation. Even though it's described in chemical terms, gee, guess what? There's electricity going on. Whenever you have a chemical transformation of one kind or another, there's always electricity going on. Study Chemistry 101, take it in college, and they always talk about the electron transfer, redox, oxidation reduction. There's always a transfer of electrons, one way or another, that take place. And it's no exception in any chemical process. You can't avoid it. Electron activity is there. And so this behavioral characteristic of the chemistry, it's hard to imagine the same thing ain't happening in the electrical backdrop to the peroxide breaking down. It's pretty hard to think that it's not happening in the same manner. Because in order for the chemistry to decompose at a faster rate, the electron transformation has to occur at a faster rate as well. So when you get a circuit such as, if I can bring it up very quickly without costing you too much time waiting, in a circuit that can do something similar by creating reactive power in here and accelerate at a logarithmic rate so that you only have to wait. Let's see if I can find the let's see. Well, this is measured in 4 seconds. So in 800 milliseconds, there's already indication of a good deal of surge taking place here. All right? And this is RMS, right? This is, this is RMS. What is this, voltage? No, amps. This is amps or voltage? It doesn't. No, amperage. So this is RMS current of load number 3, which is the inductive load, the DC inductive load. So it goes through the transformer, goes past the capacitor, the 1 picofarad capacitor, and then with the DC inductive load, the amperage rises quite well, so that by the end of 4 seconds, we're up at 122 amps. But it rises, it takes a little time. See this rise? Now let's see if we can get the one that I want to look for. Whoopsie. How'd that get there? No, this is not it. I want the... where is it? Oh, these are nice slides I got. Oh, there it is. So this is the raw output for the resistive load, right? No, yeah, load number 1 is my resistive load. Volts is in blue and amps is in red, and there's a 1.67 ratio difference between the voltage and the amps because the resistor is 1.67 ohms. And this is not next to the transformer. This is next to the, let's see if I can bring that back up again. This is here, this resistor right here. So let's blow this up so you can see it. This is this resistor right here, 1.67 ohms. And I chose it so that you could readily see the comparison between the two. But this is raw, peak-to-peak voltage, you know, no RMS involved here. And you get I like to call these staccato wedges, because if you did an in-depth view of this, let's see if I have that. Yeah. Then you see that the blue here, the voltage, and the red, the amperage, they're totally lined up, despite the fact that they're being fed by reactive power being transferred to this coil from these 4 coils here at a 10% coupling coefficient. So the coefficient of coupling is very poor. It's no different than a rotor inside of a single-phase induction motor, by the way. Whoops. But it creates, that's the short, you know, the close-up view, but in the far-away view, those waves, and by the way, they're triangular because the simulator can't do any better. You know, it doesn't mean the simulator is broken. It just means that as the energy surges, it raises its frequency, and the simulator has a hard time keeping up. So it's not broken, it's just strained. And so instead of showing a nice sine wave, which you'll see at the beginning, if you do this analysis at the very, very beginning and scope in real close at the very beginning, you'll see the sine wave. But after it's been going on a while, the simulator can't keep up with the acceleration of frequency, let alone, that's going on along with the acceleration or the increase of power and the acceleration of surge. The surge itself is accelerating, but the frequency is accelerating as well. Everything is going up. And so the simulator can't keep up, so the best it can do is create a triangular shaped wave to approximate a sine wave, but it shows that they're in phase. It's totally useful energy. I did an in-depth analysis to make sure I made certain I was performing my function, or my goal was to use Oliver Heaviside as my example, and I didn't even have to use Oliver Heaviside for a resistive load, only for inductive loads. So it turned out to be I only needed him for half the problem, to solve half of it. But be that as it may, when we take a look at these surges, they rise. Look at that. That is a hyperbolic curve, indicating a logarithmic rate of growth of voltage and amperage. And then suddenly it cuts off because I use a solid state device, a spark gap, as my means of cutting off the surge by dissipating it, by radiating, by losing the energy through radiation. The spark gap gives off radiation when it fires, when it arcs. And it's microwave radiation, so you got to protect yourself by putting nested Faraday cages, layers of alternating foil and paper plastic to protect anybody nearby so they don't get rheumatism in their fingers and end up siring mongoloid children because their testicles got bombarded by too much microwave radiation. The military already figured that one out by testing it on their soldiers without telling their soldiers what they were doing to them. But be that as it may. So this is the nature of a surge. But here I am wondering, well, I went to Stack Exchange to try to find confirmation because I didn't know, and I still don't understand, why it happens. This doesn't explain why. It just says this is the way it is. But here's confirmation for what I've been looking for. Confirmation that what I'm seeing is real, and it's not a byproduct of me breaking the simulator. This is real stuff in the real world that happens chemically, which means it happens electrically. And anything that can happen electrically as well as chemically can happen electrically all by itself. You just need the right circuit to do it. And of course, there it is. It happens. This is a $5,000 simulator. I don't have the money to pay for it. I'm using, see what it says up here? Evaluation version. That's for free, I have to keep my circuits simple in order to do any kind of testing or, design, because it's free. That's the only limitation if you don't pay the $5,000 for the darn thing. And it's a great simulator because it costs $5,000. You get what you pay for, right? In today's world, that's the way it works. No such thing as a free lunch in today's world. Well, and I keep working for something other than a free lunch. I mean, something other than having to pay for a free lunch. Namely, build a circuit and you'll have all the energy you need for free. And you do so at your own risk, because the thing may blow up in your face. It's no guarantee it'll be stable with these parameters involved. These parameters only work for microcap. They won't work for LT Spice. And if they don't work for LT Spice, if they're slightly off, which they will be, I can assure you, then in the real world, I can assure you, they'll probably be slightly off. And all you need is slightly off for either the thing to go comatose or blow up in your face. But the fact of the matter is, I got confirmation. And that's what I needed. Something to make me feel like I'm not a wolf crying in the wilderness or a man of La Mancha dreaming an impossible dream. I actually am talking about something that is real, but nobody wants to go there because it's dangerous for one thing, and you'll probably lose your job for another because it's not good for the economy to come up with an actual free energy device that works. So I'm promoting something that's not good for the economy. It's great for quality of life because it'll help all the people in the third world countries raise their standard of living. Meanwhile, it'll lower ours because money will lose its value. The banking establishment will go out of business, along with all the other big corporations like Pepsi-Cola, because, they'll have to give away their product for free. They're not going to make any money off of it. And you know the way it is with natural remedies. You can't patent them, so nobody can make money off of them, so nobody promotes them. You got to figure them out on your own and go fetch them on your own if you want to use natural remedies such as herbs, such as like cayenne pepper. You see anybody patent cayenne pepper? Nah, because it's natural. Nobody can patent it, but it's a great remedy for all kinds of ills and ails and preventative medicine. My God, it's superb. Anyway, this is why free energy is not good for the economy. It's like cayenne pepper or any other herbal remedy. You got to do it on your own if you want to mess with it. And if you don't want to deal with it on your own, then you leave it alone. And you go buy a fancy car and spend a lot of money and work hard for the bucks to pay for it. But I don't have any money. And I don't have job skills to get a job, to get lots of money. So I get all this knowledge and expertise for which I can do nothing about. I can't act on it. I looked up recently to publish. I'm going to get big. I'm going to publish my in scientific journals. You know what? They all charge you money. They want money up front for you to publish your scientific paper or whatever it is you want to publish. And I figure, oh God, this is getting me nowhere. So, I give away this stuff for free as best I can. And that's the best I can do. And what can I do? It's all I can do. So anyway, this is the gist of the matter, that there is confirmation for free energy. We already know how to solve the problem of how to make it useful. Oliver Heaviside provides that. And I already knew from Stack Exchange critics that reactive power is what I thought it was. But their criticism really got me downhearted, and so I thought, you know what? I still need confirmation, and here it is on Wikipedia, the one place that does not allow you to talk about free energy without calling it a scam in the same breath, or else they wouldn't call Tesla's electric car a hoax, which it is in a sense, but not really in a sense. It's just not exactly the way we think it is, but it did happen. It's not a hoax. It's just it happened several decades earlier than the purported story gives to us, and not exactly the way it happened either. But it did happen. Anyway, be that as it may, I think I've said enough. Oh boy, I hope you enjoyed this video. It sure did arouse my excitement. So I blew this up so you would see it. Let's see. Let's get a shortcut link fabricated so that you can easily look it up. Oh, I'm not on the internet. Sorry. No can do. You'll just have to look up self-accelerating decomposition temperature on Wikipedia or Google it, Okay. I keep forgetting. When I have to tape, I'm not connected to the internet. I can't do both at the same time. My computer's limited. Alright, hope you enjoyed this video.